Welcome to this talk on openGRIS. Before I get into the talk, I want to get into sort of how we came to building this. And before that, I'll just do an intro. So I lead a team at Citi, in Citi Risk actually, where we build our quant platforms and for risk. And I've been building infrastructure like this for about 25 years. Primarily focused on engines for simulation, for running models, and execution platforms. And so part of this work came out of the focus on helping quants and helping developers accelerate their experimentation pipeline. So basically accelerating their productivity. So before we go to openGRIS, I want to tell you, how we kind of came about this. So we run a lot of models in Citi Risk especially, and we needed an easy way to access different kinds of compute resources. So it could be a grid, it could be AWS, it could be our own on-prem hardware. And the challenge was that accessing all this different compute was very expensive. And by expensive, I mean that we obviously had already paid for all these pools of hardware, but it was very expensive from a developer perspective to access these different compute pools. So Symfony has an API, AWS has its own layer for orchestration and so on and so forth. And so for the average developer, and even more for the average quant, it is very time consuming and it's not their core competency on how should I access these compute pools and basically send my compute to them. So we began by using Dask, and then that became increasingly complex. We spoke to the Dask team and realized we wanted something much more simpler. So it goes back to this whole notion of how do I enable compute, how do I enable addressing compute for a very low cost. And I'll tell you what that standard looks like. So we began with that whole background. So we first implemented this internally as a tool for our own usage, and we wanted more people to contribute to it because we realized how hard it is. So we went to the Citi open source office and said, hey, help us open source this. And Radian, who's right here, who's the sort of the main force behind this standard, he said, gee, this looks like it'll be a great candidate for a standard. And internally I groaned. I was like, no, this is so hard. But he convinced me, and it's been an amazing journey, right, coming here. So what is the problem, right? So what is the problem in a let's say, very narrow context from a running models perspective? So there are two kinds of, roughly, on the spectrum, on both extremes, there's two use cases. One is what we call large compute, where somebody's running a large simulation, generally overnight, and using a lot of cores, 10,000, 20,000 cores, and they're going to some dedicated grid. It could be AWS, it could be Symfony, it could be anything else. And the other extreme is running what we call small compute, for lack of a better word, where a quant was sitting during the day, he's in a Jupyter notebook, and he wants to run something on a portfolio. And it might take him 2, 3, 4 hours on his machine. And he just wants to run that thing. He just doesn't want to go out there and bring up something on EC2 or have his code go to Symfony or whatever. He wants to hit enter and have it run. So all of our compute use cases fall between these two extremes. Either it is small compute or maybe slightly less smaller compute, medium, and then going to this really bad job that runs for 4, 6 hours on 10, 20,000 cores. So basically, we want to enable all of these. We want to lower the transaction cost. We want to lower the barrier to to access this. So I call this scalable compute. I'm sure there's a better name for it. And what scalable compute means is I can easily take my computation. So think of Python, think of the closure. I have my data, I have my function, and I say, send this somewhere where I can run it on a lot of cores. And I don't want to get into vendor APIs. I don't want to write to one cloud provider. I don't want to write to one grid provider. I don't want to do all this scheduling and orchestration. I just want to send this compute, have it go out there and come back, right? And also, I don't want to have a static grid. I don't want to have a static bunch of servers running all the time, like a service that is servicing me, because that defeats the whole idea of on-demand compute, right? So if I have a statically allocated grid, then that is very, very wasteful. So what you will see in a lot of large institutions, financial institutions, is they have a lot of cores, and they have 30-40% utilization, which again is very ineffective from a cost perspective, but also very bad for the environment. Okay, so that is what I call scalable compute. I want to easily address my computation. So we have a very rich environment in most institutions. We have grids, we have cloud providers, and we also have a fair amount of on-prem hardware. It could be sitting as on OpenShift, it could be VMs, it could be physical boxes. And on the right-hand side, we have a software ecosystem. And I'm kind of staying with the Python ecosystem for now to keep it simpler, but you can have a far more there. So you have Dask, of course, the old venerable Dask, and Ray and Spark. And there are some challenges with this environment today. So it's not a question of cost or access, it's a question of inefficiency. So a lot of these providers, each of them have their own APIs. So Amazon has their own, Google has their own. There's a fair amount of overlap. And then you have enterprise grids like IBM, they have their own APIs. And so writing to each API is very problematic and is beyond the scope for an average developer and definitely a quant. And on the right side, these software ecosystems, they are designed for certain kinds of domain-specific workloads. And increasingly, all three of them are focusing on what we call out-of-core data sets. So very large data sets that won't fit on a single node, and they are running, let's say, fairly small compute on very large data sets, right? So again, that's problematic. These tools also don't provide orchestration and scaling. So you have to run them on a bunch of, let's say, instances, and then tear them down afterwards. So they don't have built-in ability to say, I'm going to add more instances as my task queue gets bigger and bigger. So that's the problem, and there needs to be some kind of a bridge between these two. So what we're really looking for, and to put it somewhat, let's say, simplistically, is we want a way to route compute to the right pool. So we are looking for an analog for TCP/IP. So what TCP/IP could do for networking, we want something similar for compute, where we can say, here's my compute job. I have a bunch of resources. I have access to this grid, to AWS, et cetera, and find me the best pool right now and execute this, right? So that's the proposal. You want a standard for grid resource scheduling with client and worker standards to allow clients to send the jobs and workers to compute them in a cost-aware and user-friendly interface across different pools. Right? So it's a bit of a mouthful, but that's the standard, right? So you want some way to go between all this. Very much like, TCP/IP can route between different networks. So you give it a packet and say, this packet goes to Dropbox, and it gets there, right, eventually. And if it fails, it lets you know. So that is the idea. So what does the wish list look like here, right? So on the left, we have a bunch of challenges. For example, I want one way to access all these things, or to put it another way, I don't want to write to each of these providers one by one. And the same workload can run on Symfony in the morning and then AWS in the evening, right? That would be really nice. So I don't want, I want a single interface. I don't want static grids, and this is a really big problem that leads to different teams in different institutions, in the same institution, having their own dedicated grids, because they don't have a way of saying, I only use the grid from 5 p.m. till 4 a.m. for doing risk calculations, and the rest of the time it's available. But please be off this grid by 4:30. So there's no clean way of doing that, so you have statically allocated grids. It's a huge problem. The other problem is cost-based scheduling. The average developer or the average quant who's doing this, they should not have to figure out right now I should be able to use my on-prem hardware because it's available, or it's not available, it's completely loaded up, so I should go to AWS. Or maybe Symphony is available, and that's a fixed overhead, so I should go to Symphony instead of going to AWS. So cost-based scheduling. Time-based scheduling, we already spoke about that, where people can make their grids available between some hours. And then when the bell tolls, when it's 6 p.m., everything is preempted. Everything is harvested, and the grid is made available to the dedicated processes. Of course, multi-language bindings. I think I have time-based scheduling twice. And of course, multi-environment support. This is a very big sticking point where different teams have different requirements. So they might have their own versions of Python, Pandas. In our case, we have internal libraries for quant calculations that have different versions. So somebody wants to use 5.6.2, and somebody wants 6.3.1. So you need to be able to run their work in their Docker environment. So what needs to happen is when you run something, it says, Ridian has configured his environment for this workload, his config files, say, use environment, Z. So it'll bring up that respective Docker on the node, which could be AWS, it could be Symphony, run his task, shut it down, bring him back the compute. So multi-environment support is a very big challenge, and that's one thing this standard should also solve for. Okay, so that is the background, right? So what we are contributing to FINOS is, number one, we are contributing a standard called openGRIS, and the standard should be vendor neutral. It should provide an ability to route compute, and with compute comes some storage objects. So we will route them to different compute pools, and we're also contributing a reference implementation called Scalar. On the bottom, we have two libraries called Paragraph and Parfun. These are libraries that allow implicit parallelization of Python code. So we're also contributing those because, again, the goal is to increase quant and developer productivity. So you can basically go into your code, decorate it, and it will parallelize it. It won't be as efficient as hand parallelized code, but 80-90% parallelization is possible. So that's the contribution, and now I want to dig into openGRIS for the next, let's say, 10 minutes, and then we will have about 7-8 for questions. Okay, so the way we came to this was we first built a solution for us, and then we kind of backed into a standard. And the more and more we look at it, we don't think of this as actually, let me go to the next slide. We don't think of it as a scheduler, we really think of it as a router, right? Or something in between. So here, what we are seeing is on the left, you actually have clients, and the client is sending a stream of tasks to the scheduler, which then, based on the client's policies, it will send it to either Symphony, IBM Symphony on top, or AWS on the bottom. And those two pieces called adapters, they're the most critical pieces. So in the case of Symphony, which is itself a very rich and complex system, which does the scheduling for you, it manages the nodes for you. We don't clearly want to get to the underlying hardware and start managing the hardware that Symphony already manages very well. So in that case, that adapter would be very simplistic. It's basically a slightly more complex version of a queue. It gets the tasks, it pushes them in, and Symphony does all the work of figuring out which of my 10,000 cores is actually available, which of them can run this version, this image, the Docker image, and it will bring that up, run the workers will connect to the scheduler, and it can then actually distribute the tasks. In the case of AWS, it's far more complex. This is AWS EC2, right? Not HDC Grid. So in that case, it would actually need to orchestrate, bring up the images, again, based on what the client's configuration is. It'll bring up his or her respective images on the instances, and when those come up, the workers will start getting the tasks. So for example, in our case, we cannot log on to the AWS boxes directly. All we can do is push a Docker image onto an instance, and then it comes up. So we have to instrument that image to bring up the workers and connect to a scheduler that will give it the tasks. So that adapter will take care of bringing that up for each client, one by one. And then when those workers come up in each of those images, so let's say you bring up EC2 instance with 60 cores, you configure it for 60 workers, they will now connect to the scheduler and say, give me the tasks. They'll get the tasks. When it is done, it will shut them down. When the client's job is done, it will shut down the node, shut down the image, and is gone. So currently, we have these two pieces working. The AWS piece is working pretty well. And the next step for us, right now it is working in a static configuration, which means that each client has to configure the image type and the number of instances. In the next version, we plan to actually go to dynamic scaling. So the adapter can scale the number of instances based on the queue size. The queue size is much bigger. It can just keep bringing in more and more EC2 instances and then scale them down when the queue size goes down. So that would be very, 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 very useful. And then we also have an object notion where the data, when you're submitting this workload, currently it figures out the closure, figures out each object, and it calculates a hash and then ships off the object. And then when the workers are running, they're actually looking up the hash in a local object cache. Systems like Symfony have a very rich interface for that. So the adapter would have to interface with the storage system on that grid and basically map into their object storage mechanism. So we don't want to, again, recreate what Symfony has up there. We want to plug into it. So the object mechanism caches all the data coming in and makes it available to the workers when they need it. So that is the rough overview of each of the components. And now we can go back to this. So you have a client that submits the tasks, scheduler/router, it sends the task to the workers. Very importantly, it retries the task if the tasks have failed. And so that's something that can happen when you harvest the jobs on a grid when the time runs out, or the time policy now says this grid can no longer be used. So when the tasks are harvested, it will retry. It does balancing, and then the workers announce, when the workers come up, they announce what kind of work they can process. So they announce they're part of this image environment. They can take tasks for that image. And then object storage, we already talked about that. And finally, the butler. The butler is a very, very important piece because the butler is the one that actually works with the different compute pools to orchestrate what is coming up and what is coming down. So for each compute pool, so let's say we now had to adapt this for Azure, or we had to adapt this for Google Cloud, they would have their own adapter. And the butler would talk to that. And that's something that you need because we want to make the scheduler as lightweight as possible and really offload all the pool-specific semantics into the adapter. So that's why we have this notion of scheduler, butler, and adapter. Okay. How are we in time? 11. Okay. So this is evolving, but this is the latest one where we are talking about which piece in the system talks to which piece. And so for each of these check marks, we will have a component, we'll have a protocol. So here are the main pieces: the worker, the client, the worker, the scheduler, the butler, and the object storage, right? So this is talking about between all these pieces, who talks to whom. So wherever there's a blank space, there's no communication between them. So for example, the client doesn't talk to the worker directly. The client doesn't actually even talk to the butler, and so on and so forth, right? So that way, we can minimize the component pieces. Okay. Then what will this standard support? So from a compute perspective, we will support tasks and graphs. And the graph part is very important because we want to be able to push the whole DAG of computation into the scheduler and let it figure out. So previously we had that work be done in the client, but if you really want performance, then that graph computation has to be done in the scheduler. And this is an idea that comes from, I mean, it's a very old idea, but it was done very well in Dask, where you could give it the whole call graph, and it will figure out the dependence and do it for you. So we preserve the semantics here, very similar to Dask. So you can push a task into it, a stream of tasks, or you can push a graph into it. And if you go back to these two client sources that we also open source, ParGraph and ParFun, they actually do that. So ParGraph allows you to take a whole program, tag it, and it will automatically build the DAG, and then it will push the DAG into the scheduler. Object storage, you can right now the object caching is mostly implicit. You want to expose the object storage mechanism so you can preemptively also push objects into the compute pool storage. The semantics, we need to see a few more use cases to figure out the best semantics for it. So that's clearly under discussion. Tagging. So tagging is something that was requested by both NVIDIA and Intel, where they want clients to be able to tag the workload as needing GPUs or needing wide instruction sets. So then if you have GPUs available, it can route that to the right pool. So this is, again, going back to the whole notion of when you have packets and you tag packets and say this packet needs QoS. If your router supports QoS, then you will get that. If it doesn't support it, you will not get it. So we, again, going back into the flavor of I want to tag my compute task with what is needed and let the scheduler figure out is it available or not. Again, the goal is to free the developer and the quant from doing that manually, right? And on the bottom, compute control primitives. This is from the butler perspective. Okay, so today, this is what it looks like. Client can push tasks out into Scalar. It can go to either a worker directly running on on-prem hardware, or it can go to an EC2 worker, EC2 adapter, which will then actually bring up an EC2 instance, or it can go to a Symfony worker adapter, which will go to a Symfony scheduler, which will then send it to the Symfony workers. So the more we interface to existing compute pools, the more layers you'll have. And again, this starts approximating more and more a routing interface. Object storage, very self-explanatory. Clients, the client side of the library ships the whole closure. Objects are turned into hashes. They're stored in an object storage, and then they are sent to the workers. Okay, so to go back to this, what we have been able to do today is on the right side, we have taken a lot of our internal model computations and pushed them onto AWS. And on the left, we're just rolling out our first large, long-running compute, which can also use this. And what that does fundamentally is it really reduces the code that lives in these compute tasks. So the code becomes very simple, basically by adding between less than 100 lines, sometimes less than 10 lines, you can enable compute. So a lot of quants can actually enable workloads by adding 3 to 5 lines of code to their Jupyter notebook. They clearly need to have a scheduler running somewhere, so that needs to be set up. That's not automatic. But if they add those 3 lines and the scheduler running, they can basically enable a lot of their workloads to access AWS or Symfony. Okay, I think I'm 5 minutes left. So I'm going to skip over these. So roadmap, we are right now working on so that actually the static EC2 adapter has been finished a bit ahead of schedule. It is fairly specific to our use case and the environment we have inside the bank. So we haven't yet open sourced it, but the next step would be to do that and make one that is more generic and open source it, and also work on the multi-language bindings and then time-based scheduling. So that's the next 3 priorities. So where we need a lot of help on is for teams to help us drive the standard. Like what should be in this and what should not be in it. We want to keep the standard as light as possible, and we want very active participation from the cloud providers, from the grid vendors, and colleagues in other banks who can adopt this. So that's really it. I have 4 minutes left. Any questions?
Ritesh, when are you publishing the code? When are you publishing the code?
So the code is already, for Scalar, the code is already open source. It was available on Citi's GitHub since last November. And now,
The piece that connects to us.
so the piece that connects to you right now, what we have is very specific to our environment, right? So we want AWS help to make a more generic adapter for EC2. That would be widely useful, because we have a very specific environment internally that is not very common outside. So what we have is very internal specific code for the AWS adapter. But the code is available. I think this last weekend it migrated to FINOS repositories from Citi repositories, so it's available. And yeah.
Docs there, I don't see any code. Maybe I'm not looking in the right place.
Yeah, maybe I will connect you with the at least the legacy repositories which are current as of last week on the Citi side. Any other questions? No?
Keep my questions for the last.
Okay, but please ask them.
What's your view for integration, like going forward? Like, does that mean every single either grid or cloud vendor that you connect to, you're gonna have to build an adapter for this? Which I've already done for the other cloud providers, so why would somebody do that?
They would do it if this gives them an easier way to push compute onto that pool, right? If they're already on it and they're happy with it and there's no pain factor, clearly makes no sense to do this. So I think it'll be use case driven. So we built this because we had a use case and we couldn't use the existing infrastructure. And the last thing I wanted to build was a scheduler router. And I told the story, actually, pushed back really hard on my team for building this until we had jobs failing. So then we spoke to the Dask team and they said, yes, you should do this. So it's really use case driven. And I think going forward, it'll be use case driven because it requires resources to actually build these things. So yeah, as that shows up, we will work on it. And if there's no demand for it, there's no point building it. Yes, please.
You spoke about EC2 native, but you mentioned containers. Are you using EKS, Kubernetes, or across the clouds?
Sorry, say it again, please.
You spoke about EC2 native, but then you also mentioned containers. So are you using containers on EC2 or containers on Kubernetes?
So we are using internally. The question is, are we using EC2 or are we using EKS? Yes. I believe we're using EKS. Right? So the way it works is we push these containers out and then they are bought up. But if I give you the two use cases, the right one, the small compute, you're not bringing up a fleet. You're bringing up a few instances. You're bringing up a few hundred cores, and then you want to scale it with the workload. So EKS might be overkill, but I think right now we're using EKS. So I think I'm on time. So thank you very much.